So, let's get started. I hope you have a good break from the National Day holiday. So we will continue our random variable journey, which I believe I talk about things in continuous random variable. But before we do it, let's quickly review what we have done. And hopefully we will, maybe next week, we'll finish this whole big topic. Probably next week we'll finish the big topic. So just to remind you what we are doing is the random variable is to assign number to outcomes. And this number is usually things we care, or otherwise why we want to put numbers in. And usually there's some underlying meaningful to these numbers, either due to this financial outcome or this something we care, right? It's like how many engines are going to fail, or how much money you're going to make, or the price of the stocks, right? So that would be the things we care. And just remind you that there's two types of number you can do. One is for our purpose. One is discrete case, the other continuous. And the reason why with two is because of the idea that depend on the math we're using, right? If we want to use the classical way of doing math, then we have to use discrete. But if you're happy with the calculus, differentiation or integration, then you can use continuous. And we start with discrete random variable. And to describe the random variable, right? Basically we use the P function. It's called the probability mass function. Basically, this tells you that you give me a number that the random variable can be. This will give you the probability, right? So that is the main idea. Is like give the probability, right, for each number that the random variable can be, right? So there's a perfect description of the future, right? If you're measuring the future by the random variable, right, then it gives you all possible values that it can be for each probability, right? And the big F function is a case where you're asking what's probability that the random variable equal to that number or less, right? So just basically, if you look at this is stacking the P, you got the F, or you unstack the F, you got the P. That's what you do in the kindergarten, right? Just making a tower and destroy it, right? This is the main big thing. And if you recall, I mentioned that P is more fundamental, but F is more like artificial. But we still talk about F is because of we will do F in continuous. So that's build up the idea why we want to do F, right? Because P is undefined, or in the continuous random variable case, because P is 0 everywhere, right? So suppose the idea is you pick a random number from 0 to 1, and any particular number will have probability 0. So that is the idea. There's no particular number that you can assign probability to. Okay. And next is we call about expectation and variance, is because P and F is too complicated, right? So it's like a full set of data. Then you want to have some idea what's going on. Instead of the P and F, you want to give the expectation to summarize the P, right? P is complicated. E is the single number that tell you what's happening in P, right? Just the same idea, right? You tell me how the stock may look like tomorrow, be complicated, right? But I want to care about the expected price, right? That would be something that you want to know, right? The single number that summarize P, and you want to look at how good it is that is the variance, right? That's the same as what we have learned, right? And do remind yourself that what the expectation and the variance is actually is the mean or the variance, right? Basically, you run this experiment many times, look at relative frequency. This is what we have. So that means that your random variable has to be numerical in nature. If your random variable is assigned in ordinal case or categorical, then your mean and variance will not mean a lot. And there's a linear property for expectation, and also there's some quadratic property of the variance. And I'm not going to elaborate because I think we reviewed that too many times already. And then we also talk about bivariate random variable, which allow us to talk about multiple stocks. And particular that would allow us to talk about expectation of some of expectations, and another independence. Some of the variance is variance of sum. Okay, and this only hold for independent. And if you are not independent, you have to add back two covariance. This part, two covariance, we will learn in a great detail in the investment class. So I just highlight here. If you want to know more, then it will be something that beyond the scope of our class. So I'm not going to talk in detail. And instead, we will point you to 5 important distribution that you will be often used in applications. Of course, there are way more than 5, but I just point out how we use 5. And then based on your knowledge on this 5, you can easily extend to more you want, because the idea is same. Just learn what it is, what's the P function, what is the mean, what's the variance, and that would be usually a sufficient case, right? So the uniform will be every outcome is equally likely. So the P is very simple, right? And the Benoni is more interesting, right? The Benoni is asking us to view the world in the future has only 2 choices, either success or fail, right? Just one of them. And the P, remember, is fully describing what's going on in the future, right? 1 is P and 0 is 1 minus P. And this is the thing fully describe the future, right? Because you feel the world is that simple. And we have a technical definition of big P. It's like this one, right? And you can use the F as well, but we're not worried about this part for discrete. And do remind you that this P is not, is too complicated sometimes, right? So sometimes that's why you look at the mean and the variance, which is P and variance P1 minus P. We explain why the variance like this formula, because if P is close to 1, there will no uncertainty, right? Because always success. P is 0, then it's always fail. So the highest is like half of them are success, half of them fail. Is the most uncertain case. It's most variability because a bunch of 0 and 1 and equally spread out. And that gives us the foundation to talk about binomial, where you think about the future consists of n different trials. Okay, and each trial has success probably P, right? And the random variable is success or fail, right? You can imagine that this is the case n may be number of days in the future, right? Success or failure will be stock price go up and down, right? That is how you may model the stock market, right? Or you can imagine that n is the number of customers you're going to meet in the next hour, right? Each one who pick up the phone call, if you try to say each trial is a phone call with success P, then you ask how many phone call can be converted into sales, right? With some successful probability P, right? Then the P function is kind of complicated with a combinatorics NCX PX 1 minus P raised to the power n minus x, right? This is the P function. And as we said, this P is complicated. So sometimes we care more about the mean and the variance, right? Which is NP, the variance NP times 1 minus P. And remind you why with NP, we just binomial, it's sum of Benoni. So if sum of n Benoni, so it's NP. That's why variance NP times 1 minus P. It's not n squared. The reason is not is adding, it's not multiplying one outcome. Okay. It's not you have one outcome multiply n times. It's adding n times. Okay. And we have run for this example of how many customers out of the next 5 customers you would like to have the spicy food, and then that's tell us that active 3%, if no more than 2 customers like spicy food. It implies application-wise is if you're the owner of the shop and you know that you only have 2 portions of the spices, then 83% you don't have to run out, so probably you don't have to replenish that fast, right? So you can basically say, wait until today will be okay, right? You can do it tomorrow, right? You don't need to speed up the shipping because faster shipping probably will cost more. So basically, 83%, you're pretty much safe, okay? And we also mentioned take this n binomial into infinity, right? And when this goes to infinity and p is very small, then it becomes Poisson, right? The idea is and trial can be considered as a period of time, right? How long you're going to consider how many customers coming, and you cut y n go to infinity is to cut the future into very small time interval, right? And each time interval, that only one people would come, and Poisson will just fit. So that's why it's arrival of something is something we care, and MP is the mean is how many people would arrive per period of time. Okay, so in this one, the mean and the variance the same, and the formula given by this Poisson is coming from this exponential. We not the proof, but the interesting part is if your data look at how people arrive, have same mean and variance, that means the Poisson is very fitting what you observe. And if you look at application, there's a lot of cases that Poisson is a good fit. So that's why we have to talk about this. And then the example we give is how many customers arrive within certain period of time, right? So that would be a very useful in practice as well. So the next one we cover is after the Poisson. The Poisson is taking the binomial and n go to infinity, right? And hypergeometric is in another case is actually talking about small n instead of n go to infinity, right? When n go to infinity, when each trial is the same, then this is one direction. The other is come on the idea that when you draw things from the population, from a big set of data, then you will draw it without replacement. That is how you do audit. You do quality control, okay? Or actually do marketing, right? You talk to one person, then the person is gone, right? And you can't, you not talk to them again. For example, you try to you sell the good to do a cold call or do a phone call to the customer. Once you talk to him, then probably you can't talk to him immediately, right? At least not now. So here gives you the idea that how likely that within n big N object, and you know out of them A is good, right? Then if you just draw one, the probability of getting the good item is A over N, right? But if you don't put it back every time you draw the item out, it's just simply binomial idea, right? But now you put it back, that means that it's no longer independent. So you have to use a rather complicated formula like this one is 3 combination, multiply and divide each other. So this is a slightly little bit more complicated. I don't expect you to know the formula by heart, but you need to see, because the P is complicated, do remind you that this is complicated, but P and the variance is easy to calculate, right? Because same as the data, right? It's hard to understand data by itself, but you're able to understand the mean and variance. And the mean is just NP, right? Because, right, if you draw only one guy there, how likely that you get a good outcome is A over N, right? So that is the first part. The mean is exactly the same as you expect from the binomial. And this second part is, remember, is NP1 minus P, right? So this is same as binomial as well, right? But you have a error term here. Okay, this is called the finite sample correction, right? The variance, which means this is, you can see, this is less than 1, right? This guy, right? So what does that mean is, if you are drawing data from the sample that you, without replacement, the variance is smaller, right? Because when you draw things, when you keep drawing, there are fewer and fewer stuff, right? So the variance cannot be a lot, right? And when n is very big, right, then that means that when n is close to n, right, this is very equal to 0, right? So it means that if you, every time you draw everything, right, there's no variance, right? Because suppose your n is equal to n, right, there's no variance. Why? Because you draw everything, right? When you draw everything there, then every time you draw the same, right? So that's why hypothetically this is the variance smaller, okay? You expect. And I mentioned that at what scenario you can use it is used to quality control and audit, right? And for our introductory class, we are not asking you which scenario you apply to what distribution. You'll be given in this scenario, this would apply, and that would be for our exam and for assignment. But in your project or in your actual practice in the future, you have to decide whether this fit very well, right? And you, why this fit very well, and then you like it. And this motivation, right? This setup, is this process fit what you think in the future? If not, you have to look at other distribution that fit actually what you think about how data being generated in the future, right? If you think this is how things generate, it fit very well for quality control audit, right? Because you know this is the case and that's it. But otherwise, you shouldn't use this one, right? Even though it looks fitting our application, but if your data is not generated this way, then you shouldn't do that. Okay? And not go into detail for this. So we will spend our time on new thing. It's called continuous random variable. And you'll notice this is, we go halfway over 200 slides, is 100 something here. Okay? And turn out to be, you have to pay attention because for the rest of the semester, we're doing this. Okay? So discrete, once we're done, is almost over. Okay, maybe something binomial we still use it but anyway, binomial will more or less approximate by Poisson. So the main thing you use in the second half of the course is binomial, and this continuous, in particular the bell curve. So from the bell curve and the binomial, the thing that we'll use for the rest of the semester. So make sure that you pay attention to what we are doing, because if you miss it, then you're increasing hard time for the rest of the semester. So do pay attention, even though you are feeling dizzy from your very nice lunch, especially carbohydrates make you a little bit tired. So just the first thing is, we'll immediately see the example why we can use big P, and is the following. So consider the case you would toss a coin. Sorry, you would consider random uniform case, right? 0 to 1, right? And the big P will be 1 over n, right? 1 over 2 in this case. And the F is just stacking the P together, right? So that would be the uniform. There's no problem. We know very well from discrete case. If you have two outcomes, each outcome is 1 over 3, 1/3. And you stack everything up, it's like the going upward sloping for the F. There's no problem at all as well. You increase to 4 or 5 or 6 or 7 up to any number you want. That's no problem for the F, right? It's just a 45-degree line, you can imagine. But the thing that P will be a problem, right? Because P is 1 over n, right? And when n go to bigger and bigger and bigger and bigger, more n, then this P will basically smaller and smaller until you get 0, right? Because continuous, right, means that any number is possible, right? Any outcome is possible, then n is very large, very continuous. Then basically you have a problem. Run the problem of P is always 0. F has a good shape. Right? F is still, you still do it. Okay. So that's why our main thing to describe a random variable in continuous way must be big F. P cannot do the job. You cannot say particular point, what's the probability? Because it is essentially 0. But what can you say is the probability less than or equal to that number that is non-zero in general, right? Maybe there's 0 for 1 or 2 points, but in general, this is non-zero. And because probability of a range, right? And that means that when you talk about difference is the F between the value B and A will be the probability between B and A. Okay. And 1 minus the big F is the probability X bigger than B. Okay. So that would be the idea. And the next thing is F is slightly, your head would twist a little bit. So probably the question you would want to know is there any something like P? Okay. And in general, no, but in many applications that you would care, there exists something you call small f. Okay. It's called a probability distribution function like this. Okay. And the area under the curve of f is the probability. Okay. And that connect to the big F. So if you have f function and area like this one, okay, actually means the f is the probability that x less than equal to a. Okay. The second graph is the red area is the probability that x equal to or more than a. Okay. And the third graph is the purple area is the probability between a and b will be given by this area under the curve of f. Okay. So it's like the p, right? Because the p is the height, right? It's the probability. This is area idea, right? So it is. If you learn calculus, big P and big F, so big P, small f, and big F are related by calculus. You integrate the small f, give you the big F, you differentiate the big F, you give you the small f. And our class doesn't require calculus, so I don't need you to know this is equal to differentiation and this is related to integration. And if you want to go further in the statistics, this is something you can't avoid. Okay. But our application, we don't need to worry too much. Okay. Because we are not requiring calculus for our introductory class. So this is the integration side and this differentiation, right? And if you learn, this is coming from Isaac Newton and Leibniz's notation. Okay. But anyway, we can forget about that part. Okay. If you don't have to worry about this. Okay. So last time we also stopped at the big F. Okay. Just to remind you, because it's technical, but we will be using this a lot later. Because the continuous, you can't really define the P, right? So F will be the string you see, and F something will be look like this usually. Okay. It's increasing, must be, right? Because it's less than or equal to the bigger number must be increasing. So what it means is if you pick particular value X, you go up and go left, right? This value is called f of X, right? That means that the probability, right? This is the what? This is the probability that the random variable less than or equal to a particular number, small x, right? X is some number like 10, 11, or 5, just some number, right? This f. So this f is, you give me a number, I give you the probability, right? And you learn from math, what we call inverse function is go the other way around. is go this direction. Okay. The green is going to this direction, right? From horizontal axis to vertical axis. The inverse function, which we call F inverse, is you give me the y, I give the x, right? So this, let me see if I can use the pen. This looks better. F of y inverse, maybe it is F inverse of y. Okay, you go from the y to x. Okay, you give the probability that what should be that, then you will be going back to the horizontal axis from vertical to horizontal. Okay, that's the inverse function. Here's the inverse. We will use this very often, the inverse function. So, but don't worry, we'll be using this all the time. So you must be able to see this. Okay. So graphically, it means the following. Later, you will see if I have an F function like this, right? F function is asking if I want this probability to be some number, maybe I want this to be 0.9, 90%. What is the X over there? Okay, so this is something I will do it all the time. That requires actually the inverse function, F inverse. So we do it today or we do it next week. We do this all the time. Okay, so don't worry about this part. In case you're not getting it, it's okay. Okay, so we will be doing this very soon. Just I put it there in case you want to know what's the inverse, because that's the math function. Okay. Now, although because we can't use calculus, so we'll just use the concept that brings us. Just trust me. Expectation and variance is still well defined. And I did the same. You just imagine that you run this experiment many, many times. You have many, many eggs. Of course, now it's no longer discrete, but continuous. Okay. And average of this is still well defined. And the average is still called expectation. And you can also calculate the variance, right? Every time you get the number, you minus the mean, you take a square, right? And many, many of them calculate this, is called the variance, okay? And if you care, this is the equation, okay? If you know calculus, you know what's going on there. If you don't know, you can forget about it because we are not doing the thing, but basically this thing is adding summation, okay? You just replace this by adding because if you learn the integration, right, this is simply adding summation, right? And you don't talk about the D, right? The same thing. But anyway, let's forget about this calculus because we're not talking, so this is completely technical. I'm not going to do that. But rather, we assume we know how to calculate. I just give you the result. And turn out that in our class, we will be learning all these 6, okay? Last 3, don't worry, we will be talking about this in the second half of the course, okay? But the first 3 is something we need, okay? The first 3 is often we use it. And the last 3 will be, we will use it throughout the class. Basically, actually, we will be using a lot for the last 2, okay? Last 2 we use a lot. And also the normal we use a lot. And uniform and exponential by itself already have a lot of application. Okay, so we tell you how to model thing using uniform, exponential, and normal. Okay, for chi-square and student T and F, will be very quick because you don't know how to use it until the second half of the course. But the first 3, we will use it immediately. You know how to use it and what the application. Okay, the normal, you know very well, it's a bell curve, right? You know very well. In the old days, the grading, the IQ, everything is normal, the bell curve, right? And then that's you know, right? Meant for those people who take high school exam, right? Cross entrance exam, right? You got the grade 5 star, 5 star. These are called normal distribution, right? If you're top 5%, you get a 5 star, right? this is the same thing goes on, right? But we'll be talking this in detail very soon. So let's go to the first one, uniform, okay? Uniform, we focus on the case of uniform over interval, right? Because this is something we usually modeling is, I don't know what the number is, but it must be between some numbers. And usually you don't know what's going on. Uniform is the way, right? What it is, suppose you look at the everyday the financial news in the morning, right? Often the news anchor would ask the so-called expert, what is the guess of the stock index today, right? And they will say a range, right? The lower will be maybe 2,000, 24,000, right? For Hang Seng Index, right? The highest may be 26,000, right? And lowest and highest, and then he didn't say anything which number is more likely, then essentially he's likely saying uniform, right? Each number is very likely, right? And the support from A to B, right? The smallest, right? It's just 24,000, right? B will be 26,000, right? And so what is this, right? Once you know he don't say anything, right? And each one is equally likely, right? 24,000 to 26,000, right? That means that the F and the small f and the big F will be defined the following, right? Because each number equally likely, then you expect the so-called P function, right? The big P function or our analog small f function. I mean, the small f function should be same, right? It should be, that doesn't really matter where you are, right? The small f function will be 1 over b minus a, and the big F function is a minus a over b minus. What's this? Okay, let me show the graph. So this is the graph, and I will explain this in a great detail because this is the way to understand what is the F, big F, and small f. Okay. So the small f, why is a line? Okay, this is actually you expect when we see the P, right? Go back to this P. It's uniform. It's a flat, right? So you should expect this should be translate the same. The F should be the same. Why? Remember, when this F, when you talk area with probability, right? That means that if A to what's the probability that the number is between A and A plus 1, say, right? Will be this area, right? Remember the area under the curve is the probability. So the area between A and A plus 1 will be the probability that the number fall between A and A plus 1, right? And if you look at B minus 1 to 1, okay, is this area, right? So we say this uniform, it means that doesn't really matter where you start and where you end. As long as the interval is the same, it should be the same, right? It doesn't really matter where it be uniform. You can't tell, right? Because everywhere the same. So only the interval length matters, right? So because look at the area is the base times height if for rectangle, right? So it doesn't have to be you have to be the same everywhere as long as the interval the same. It must be a rectangle. So it must be flat, right? Because no matter where you move this small 1 unit area, it must be the same everywhere. So it can only be a rectangle. It can't be a triangle, it can't be a circle, it can't be any other shape because no matter where you move the window, 1 unit interval is always the same area. It must be a rectangle. We can't think of anything else. Okay, so that's why uniform, it must be a rectangle with the same height. Okay, and the next thing you ask, okay, I know it's a rectangle. How can I know the height? Why the height is 1 over b minus a? The reason is the area is probability. So for rectangle, area is base times height. And base times height is 1. And the base is b minus a. Okay, the base. The base is b minus a. Okay, and height is unknown, right? Base times height is 1. How can b minus a times something is 1?
that something must be 1 over B minus A, right? Otherwise, it can't be 1. Let me repeat, right? Because the area must be the base times height. The base is B minus A. This times this, suppose call Y, okay? B minus A times Y equal to 1. What's Y? Y must be 1 over B minus A. Right? Because they cancel out, must be 1. Right? Suppose, put it this way. Do it more concrete. Suppose this A is 1, B is 3. Okay? And the interval, the length is 2. 2 times what is 1? Must be 1/2. Right? 2 times 1/2 must 1. Right? If B is 5, B minus A is 4. 4 times what is 1? Must be 1/4. So it must be the inverse, right? It's it times the inverse must be equal to 1. So that's why we have this guy. Is that clear? So that's how you use the continuous, use the F, right? Suppose I give the F, right? You want to know probability between these two numbers, just the area. Okay, that's the idea. Now, you will ask, okay, now I get the small f. How can I do the big F? Y is going up, right? Y is going up. But of course, you know that from the example, we know it should be going up, right? But we have to prove it, right? It's not something that we should be just happy. Okay, we believe you, right? Y is a line, not a curve. Okay. The answer is not complicated, but is that okay? I erase the board. Okay, let me erase it. Why is the case? Remember, what's the F? F is the probability that the random variable equal to that number. Okay, so that means that if I pick particular point here, say suppose I call this point C, okay, and I go up here, this is f of C, means what? This means that if I pick a point, this is the same point here, C. This area is just the value f of C, right? This is what we mean by this f, right? It's the area less than or equal to that is area, right? This is 0, so you only care about this area. Okay? The size of this area is the height. Okay? The height of big F is the small f, okay, area. Okay? Is that clear? So, how can you calculate the area of rectangle? Base times height. Okay? Base times height. You learned it in primary school. Okay? So, what's the base? Base is C minus A. Right? What's the height? We have said already 1 over B minus A. So, this height is C minus A times B minus A. Right? And let's call it generic, no longer call it C, you call it X. Right? X minus A over B minus A is what? Just a line. Right? Y equal to this, right? It's linear. You learned that from the high school, right? So that's why it's linear. And we're done. Right? Because X is A, this is 0. You put X is A. Right? You put X is B, this is 1. Right? When X is B, this is 1. Right? B minus over B minus A is 1. Right? This is B minus A over B minus A, this is 1. And this is A minus A over B minus A, this is 0. Right? So this is why it's here, here, here. Okay? It's a zigzag style. Okay? Is that okay? Well, you may worry about I wrote this, why I didn't write in the slide. Of course, I didn't write in slide means I'm not going to exam on you on this one, right? So don't worry too much about this. I explained this because I try to understand what's the F and big F and small f, right? Because I said we are not interested in asking you small f, right? But we need to know, right? Otherwise, what are you learning, right? You have, although we don't talk about math, but at least you understand how to describe them. Okay. Before we break, I think we should have an example to illustrate the power of this thing. Is that okay for this slide? Let us go to the example. Maybe the example, but just this one before the break. So we understand that the small f is not something we care, right? So only you care is the big F, right? Because small f is too complicated for our class, so this is the small f, right? When we say uniform, basically it's just a zigzag style, right? And this is something we care. It's the mean and the variance, the calculation, right? The mean, probably not surprising. It's just the smallest plus largest over 2, right? Because this we're in the middle, right? I don't think this surprised anyone, right? The only thing that surprised me still now, okay, is the variance. Is something super unnatural. Is b minus a squared over 12. Okay, don't ask me why over 12. If you ask me, I show you the proof. I have no intuition for that, but I can explain something is why b minus a. Why? Remember, variance is measuring what? How variation of this, right? And if b minus a is larger, actually the number has larger range, right? And larger range, then variance larger. Y square because variance is a square, right? So, and Y12, don't ask me, it's a math result. If you know calculus, there's a proof I put in the slide. You can do it. If you know calculus, you can do it I think you can do it in 10 seconds. Okay. The proof is, I put it there. The proof is just like, not two slide. You can actually do a proof on that. But I'm not going to do it because we're not requiring calculus for this class. If you learn calculus, it will just very simple proof. Okay. But we're not. So then I can't explain 12. Okay. Because that is, you can try to check out there's some intuition behind 12, but I'm not going to talk about that. Okay. So what you need to know, remember our class, right? Remember the purple region, purple box. This is the theory you need to know, right? And you need to know later after the break, we talk about the green thing. The green thing is required for your assignment. Okay. So the main thing I asked you is for the green, right? And if you don't understand how to do the green, the underlying logic is the purple, right? So make sure that you know the purple and know how to do the green thing. You're done with this class. Okay. But of course, I want you to know more, right? Because that would be more useful. Because if you just know how to apply, then AI can do your job, right? I mean, you're better than AI, right? So you need to know how they are being applied, right? That's more important. Okay. So let's have a break of 15 minutes. In the meantime, I want you to do the you reply. So we resume at point 2:32. Let's have 15 minutes breaks. Please fill in the you reply as a measure of attendance, participation, and also I know whether I'm going too fast or too slow. Thank you very much. Early morning.
Just between the board, but.
Oh, that's surprising.
Yeah, we were still like, oh.
Okay. We can't start the class because she's just reset by computer. I think she basically shut down the system. How can she do that? That's crazy. I have to come. I know. Just restarting. So
It's like. We didn't.
yeah, how can she do that? It's not okay. She never did it when there's someone I come to the class. I never did it. So she only did it when I was the break. She never did when I go out and I come into the class. I never did it. Very crazy. She never do it when I need when we need a service. She never did it. She did it when we don't need the service. Okay. Luckily, it's still here. Otherwise, I don't know what to do. Okay. Luckily, he didn't switch off the thing. Although, okay, maybe I blame her on it, but at least it's not done. Okay. I'm not too, so I should not complain her. It's okay. Just let her erase my plot. But anyway, let's see what can be done. Okay, luckily, we don't have to start all over again. Otherwise, the mic is too loud. Okay. Is it okay? Is it okay? Do you drink other than coffee? Yes, I do drink a lot of stuff outside coffee. I drink tea, and I also have I actually drink a lot of herbal tea because I don't know whether you guys which part of place from the earth you are from, but at least for people from Guangdong province, the Guangzhou area, we are not very used to the water here, so we always have to drink a lot of herbal thing to make our internal system work nicely. So I drink a lot of herbal tea, but you also find this a lot of them around the world, around Hong Kong, especially in Guangdong area. But the tea is the thing I do. But I only drink coffee because I teach. Otherwise, if you look for me in second semester, I don't drink coffee. I only drink coffee in the first semester, which I have a lot of teaching. So I drink 2 cups of coffee today already so far. Because of maybe I need another one because I'm teaching at night as well. So I need another one. Oh, so someone's still living in Wednesday. So make sure that you're okay. Weather, okay, rainy, but someone told me umbrella there must be. And have a geometric uniform. Yes. The difference between big F and small f, not the difference, but it's same as P and F, right? The big P and this big P and the big F can move each other. So that's why the big F and the small f, so you can, if you know the big F, you know the small f. You know the small f, and the big F. Okay. And the speed is okay, but maybe someone say I'm a little bit too fast. I try to slow down because this is a very important point here. Stack is a joke. Yeah, I think our stack is a joke, kind of. We didn't do it very seriously, to be honest, because we actually don't even go to the statistics, but that's trying to tell you how to use it. But if you really go to the math, you do the calculus, then it's like something very serious. It's not really a joke. It's more fun. But of course, you need to know a lot of math to understand fully. But at the moment, we can just do what we can do. So let's continue with this uniform. I don't think your big problem maybe beside this derivation. Here just I try to derivate from this is actually I wrote down here is basically from this guy, right? This was what I explained already. Okay. So you can see if you have narrow the A and B, then it will be higher. If you have bigger A and smaller A and bigger B, then you will much flatter. So I think this example is something that we want to know more. Okay. And this is rainfall is uniform between 1 mm to 4 mm. Okay. You can imagine this is stock market. The stock price is between this and this is uniform. Okay. Just to remind you why we have uniform, it's because uniform is we don't know what it looks like. Uniform is the best place to start. Okay. And uniform, the mean is just remember the formula. This is A, this is B, right? And for the mean is simply A plus B over 2, right? And this is B minus A squared, right? So that is what we've been doing, okay? And then you just apply, you get the mean and the variance, right? So if you apply this to stock price, right? Then you see the stock price, the stock market index will mean A plus B over 2, B minus A squared over 12, right? So this is how you can quantify your risk and return, right? Suppose you want to model the stock return like this, okay? So that's not something too difficult to see how you apply this, right? And the next question will be more fun is not just mean and variance, but I want to use probability, right? Suppose I have the probability between 1 and 4. So how likely between 1 and 3? Okay. So if you don't want to use this crazy math here, let me show you one easy math. Just do the graph. X must be between 1 to 4. All right. So this is 1, this is 4. Right. And this uniform, if this is small f, it means what? It must be this, right? It's open here, right? And what's the height of this? This width is 3. The height is 1/3. Why? Because this is 3. Okay. And the question is asking between 1 and 3, right? That means that we can just use the blue color. 3 is here. Between 1 and 3 simply mean this area. And this area is a rectangle with the base 2, height 1/3. So we have 2/3, then we're done. All right. So either you can directly use this. Actually, this is integration idea. Just integrate, right? If you learn calculus. If not, then you can use the f function, right? Between 3 and 1 is anything less than 3 minus a thing less than 1. Then that's what you have, right? Less than 3 and less than 1, then you're done. So it's 2/3. Is that clear? Okay. And anything between, this is between 2 to 3, right? So to remind you what we have, here. Hey, it's not drawing. Right? Where is it? Right, this part, right, between 2 and 3 will be the very same thing, right? Now is 1 to 4, still the same question. The height is 1/3, but now it's between 2 to 3, right? Is this rectangle area, right? Remember the base is 1, the height is 1/3, so the answer is 1/3. All right, so we're done, right? The base is 1, right? The height is 1/3. So 1 times 1/3 is 1/3, so we're done, right? Of course, you can do this idea, right? Must be between 3 and 2, right? So, or you can say the probability between 2 is less than 3 minus strictly less than 3, but strictly less than is there's no difference from less than or equal to, so that's why I can say 3 minus 2, and we know this formula, just apply, then you get the same. Or you can start from the small f, right? So this is how you do in the big F, this is how you do in small f, right? And small f, you apply integration, but integration is basically looking at area, right? So that is how you can do it one way or the other. And this is more formal, right? Because this is what you learn, right? But this is more intuitive. Is that okay? Okay. So I guess this uniform is useful by itself. And the next one is also very useful by itself. It's called exponential. Okay. It's the time until something happened. Okay. Remember Poisson, right? You're talking about something arrive, right? In 8 hours, how many customers will arrive, right? In this 8-hour period of time. But exponential is how long before that happened. Let me draw a picture. Remember our Poisson idea, right? Poisson idea is you have a time period and talk this into very small interval, right? And this small interval have a probably p that things happen. How many interval there? There's an n interval here, and n is very small, a lot, right? Then Poisson is asking in this long interval, how many of them would be there, right? And we know this how to model that part, right? Then that would be asking, this is happening, this is happening, this is happening, right? This is actually some people arrive there, right? This is, and the question of exponential is asking the following. Instead of asking, in this whole period, how many customers will come to your restaurant? You ask the following thing. You ask, how long does it take for the first customer to arrive? Right? This is what we call exponential. Okay? And one thing to remember, this Poisson is independent, right? That means that the next one is also exponential. The third one is also exponential. So the time for successive arrival in the Poisson is called exponential. Okay? So that repeat, Poisson is number of people arrive in the given period of time. And Poisson is time to take for the different arrival. Okay. So these are follow the exponential distribution. And probably the first thing come to your mind if you study physics, this is nuclear reaction. And the time for nuclear reaction to happen, follow exponential. Okay, that's why you learn half time, all this kind of thing. But we're not physics, but this is very useful. Okay, because we say Poisson is a good way to model things. And model arrival, and to model time arrival, that will be exponential. So that's why it's very useful, because everything based on binomial, right? So binomial will give you Poisson, and this also give you exponential. I hope it's clear what we're doing. Okay, it's time for things to happen. So the waiting time is the waiting time until success for Poisson with mean lambda. Okay, and as we said, because Poisson is independent, so it's memoryless, right? So that's why I said in the graph here, all these are exponential. And what the memoryless property means the following. It means that no matter how long you wait, where is my, okay, memoryless means no matter how long you wait, your probability will remain the same. What I mean is this. Technically means the following. Probability that x bigger than t. Let me write down a bit longer. X t plus a So suppose you have to wait 8 minutes, then you wait t more period is same as this. A is a time you wait already, okay? And things doesn't happen, okay? And you wait t more period, okay? T period longer is same as you start from the beginning. What does that mean? This is exactly you don't have memory. Or I would say this is exactly this kind of old history. If you go to many seaside, there's a old village, there's a mountain there, and there's a rock over there, okay? Looks like a woman, and very often there's a story saying that this woman is standing waiting for her husband to come back, and she waits year after year after year, and she become a stone. And there's many story. I think there's something in the Lion Rock Mountain next to the CTU, right? And there's a mountain there, right? Why? Way after year, because she always said tomorrow she's going to come back, right? He's going to come back, so on and so forth, right? Why? Memoriness. She forget what happened in the past. She still always say, tomorrow my husband is going to come back. Every year after a year until she died. And she didn't think if he's not coming back after 10 years or 20 years, no difference. To change your mind, right? So that is that's different, right? So turn out to be if it's a Poisson, this F look like this guy. This guy looks a little bit crazy, right? What's going on there? But if you look at this, is later you see just like exponential decay. This is something you observe. Look at the nuclear reaction things. The time thing is the beginning is a lot, but getting slower and slower and slower. Okay, and the function look like this guy. Okay, the F function is okay. And let's see the and very interestingly, okay, this is the F function, and the mean is simply 1 over lambda. Why? Give you example. Suppose if in hour, this is 1 hour, okay, which is 60 minutes. Okay, if this is Poisson with lambda, say, I know 4, means what? Every 15 minutes, expect someone to come, right? So you have you have arrival of 4, and each one is 50 minutes. 50 minutes is 1/4 an hour, right? So that's why the number of time required to wait for something to arrive is 1 over lambda, right? Because suppose lambda is 4, you have to wait 1 over 4 to period of time for it to come, right? And what is the variance? I'm not going to prove it, but that will be this 1 over 4, and that's 1 over 16. The variance is to double the time of the mean. One of the reasons is like exponential is dropping down, so is the variation is getting less. I'm not going to explain this because it's involved calculus, okay? But that is what the thing, right? Because you probably did not know this formula may be complicated, right? But this is summarized by this 2 number, right? Mean and variance, right? It's the way. Of course, you can do more. You can do kurtosis and skewness, but I think for the most application, right, we only need to know the mean and variance. Okay. So and then also explain how the Poisson connect to this formula. Okay. And I guess there's something I want to mention a little bit is for some textbook, they would use beta equal to 1 over lambda. Actually, what Excel would do is they don't use lambda directly, they use 1 over lambda as a beta. I don't know why, but same thing. Okay. Then the beta would means how long you wait, okay, for things to happen. But I use lambda because it's naturally correct to the Poisson thing, so that's why I use lambda. Okay. So later when you use Excel, you see you should be careful what you input. Okay. So that can be tricky for your assignment, right? Whether lambda or beta. We'll talk about Excel at the very end, but let's forget about this for the moment. Okay. The F look like this. Okay. And this example, okay. This is the very useful thing is imagine the customer arrive, follow exponential distribution, okay, with mean of 20 minutes. Okay. So this was probability that arrive in the next 10 minutes. Okay. So here means what? Means if you like lambda is 1 over 20. Okay. If you learn beta is 20 if you use beta. Depending on you want to use lambda or beta. Okay. But in our class, we focus on 1 over this one. Okay. The question is, arrive in next 10 minutes is this guy. Right? And this guy is just big F. Okay. You just put it is this guy, right? 1 over lambda x. This is the formula. If you remember a few slides back, this is something we need you to know, right? This is the big F function, right? So we just put the lambda, it's 1 over 20, put x10, then 40%, right? So it means that 40% of time you arrive in the next 10 minutes. Okay. If you don't think exponential, you think, yeah, it may be much less than that, right? Because the mean is 20, right? You think within 10 should be much smaller, right? Because you think mean in the middle, right? If you think mean is same as median, right? Which is not the case, but if you think it's the case, then you should be thinking much less than 40%, right? But exponential, it means that most of things happen before the mean, right? Because it's a right skewed distribution, right? So everything is the mean the mean is bigger than the median, right? So that's why that's why it's like this. Okay. And we have the other example asking how likely that between 5 minutes, 20 minutes, 50 minutes. Okay. So the question is like this guy. Right. So if you want to see, right, it's basically this, right, asking 15 or 5 this area. All right. And how to do that is you can use the idea of big minus small, because F tells us the area on the left hand side. So you can find the blue is looking at the green area. The green area is F15. And look at the pink area. The pink area is F of 5. How to find the blue area? Green minus pink. Okay, green minus pink is blue, and blue is what we want to find. Okay, so that's why we have this is the idea we want to do. Okay, don't forget about this. We will do this. Blue is green minus pink a lot. Okay, for the rest of semester, we'll do a lot of this area subtraction. Okay, so we figure out this 30% within this region. Okay. Okay. So as you see, exponential is doing time. So that's why there's a lot of application like modeling how long it takes to complete the thing, right? And how long does it wait for things to break down? Okay. And how long do you need to wait before some new customer arrive? Right? All these things can be easily modeled by exponential. Okay. When model time is a concern, exponential is often the first choice. If Poisson is the thing that good fit for your arrival. Okay. Of course, if Poisson doesn't fit, exponential is wrong. Okay. But I'm not going to do this application because I know you can read it by yourself without further problem, because this is just redoing the example again. Okay, but with different setting. Okay, so we shouldn't be too much surprised what we're doing here. Okay, now the remaining 50 minutes, let me have the honor to introduce you the single most important thing you will learn from this class, the bell curve or the normal distribution. Love it, hate it, this is the thing you remember for the rest of your life, I think, because this is the nightmare for this class, is the bell curve. You do the bell for all time. Luckily, CHK has adopted criteria-based grading, so the bell curve no longer relevant to your grade. But before that happened, bell curve is the thing we do all the time, right? Because later you understand why the bell curve should work. Most of the time, because what we call the central limit theorem, we will learn next class. Sorry, next week, I think. Or the week after, is saying that if things are determined by many small parts and each part is random, you will see a bell curve. That's a mathematical result. Is if things are from different random thing, you will see a bell. Bell is something natural. That's why IQ, height, weight, marks should be bell curve. Right? The reason why the bell curve shouldn't apply in CHK because you guys are the best of the best of the best, right? So since the best of the best of the best, the bell curve doesn't apply. Why? Why the bell curve apply before you come to the college? Well, because before you come to college, everyone follow a bell curve, right? Because the IQ, your exam determine from the IQ how much time you spend on study, how well is your classmate, how well is your teacher, how good is your day you have performed in the exam, and many things, right? And these all things are all very random, and your ultimate performance should follow a bell curve in aggregate. But we only, in our B school, we only take the best of the best of the best of the best, right? So you're here. And once you take out this part, it's no longer bell curve. So that's why we no longer use bell curve. But the bell curve still apply when you come to the college. Okay. So that's why I think that's the reason why CHK dropped the bell curve, right? So we no longer have a rigid percentage of who get what, right? But you still see the bell curve when you go to public exam. But you don't have bell curve in the school. Like when we have 70 students in our class, right? Or 100 students, the bell curve doesn't apply very well. But if something going to take on CHK, I think we still have bell curve, right? But within a small class, I don't think a bell curve is a good thing. Okay, so that's the reason why we don't have that. Now, the bell curve, now we know why we have the bell curve, right? Because things come from nature is a bell curve. But things is not come from nature need not be a bell curve, right? If I explain why a bell curve. If things come from a lot of natural things, a lot of randomness, bell curve is a result. Okay, it's a math result, and we know it for very well, right? Just look at all the animal, look at all the insects, right? All the insect or animals you look at in the zoo, right? They're not the same, but most of them follow a distribution looks like a bell curve, right? Suppose pick an animal, try to look at the things in the forest, look at natural environment, they should follow a bell curve. But in business, it need not be the case, right? Look at stock price. The stock price is the result of human interaction, right? So that's why if you think stock price follow a bell curve, you make a mistake. And actually this mistake costs a lot. That is the reason why people said 2007. It's a big mistake. It's because they think about the stock return is a normal. And thus they derive all the Bessel's equation, all the thing. And that's why now this is Bessel still work, but you have to need some do modification because it's not exactly a bell curve. When it's not exactly a bell curve, that means that the kurtosis is more than 3, right? And you have the fat tail, and then things have to adjust accordingly. But in our class, we do not worry about this much. We'll still do a bell curve thing, okay? So the bell curve turned out to be, the F function is something that is a nightmare. Let me like this. You ask, what's this crazy thing? Okay? And don't worry, you don't need to memorize this. I'm not even putting this in the blue thing. So just feel free to forget about it, right? But if you can't sleep tonight, it's good to take it out and try to see it 10 times. Then probably you can remember. Okay? But what exactly is this guy? What exactly is this guy? Okay? I'm not going into math, but turn out that this, if you don't want this to be crazy, okay, this is simply, if you look carefully, this is simply this. Maybe I just use X. This. Okay, this guy, you said mu to 0, sigma to 1, get this guy. Why mu to 0, sigma to 1, this guy, I'll explain later. Okay, we will look at this when this happened. This called standard normal. We will talk about this very soon. But this guy, you ask why this guy. Okay, why this guy? Okay. And you ask why this normal. Okay. Think about this. Why this so special of this is if you think you want to have a 3-dimensional graph, okay? This is the map, okay? You try to build this is a hill, right? It's 3 dimensions, so we just look like this. I don't know whether you can imagine, okay? It's a bell, right? If you want the bell to be a perfect symmetrical thing, Okay, doesn't really matter you look at which direction you look at. Okay, and the only mathematical probability that if you want this shape, okay, a perfect sphere, okay, and turn out that if you do the math calculation, turn out it's removed. It is only possible. Is the formula only possible is this shape. It doesn't really matter where you are, and this is the only feasible. Okay, and if you don't get it, doesn't really matter. But this is only where special property is like. Really, the shape is like no matter where you cut the thing, okay, it's three-dimensional thing. No matter where you cut, it's the bell curve. Okay, where you cut doesn't really matter. Okay, where you look at the 360-degree, the same, always the bell. Okay, you get this guy. Okay, and probably don't worry about this math because this is the thing you never use it. Okay, and let me tell you, there's a two number very important. It's called the mu and the sigma, which I will set mu equal to 0, sigma equal to 1 in special case. And what is mu and sigma? And if you see the notation, mu is actually the mean of this. Okay, and sigma square is exactly the variance. Okay, so if you have the bell is at 0, sigma equal to 4, look like the red one. If you keep the same mu, increase the sigma, this is F, okay? This is the height, this is F, okay? And the bell will be a deformed. You can imagine the hammer, just keep crunching it, okay? It will become flattened, okay? Remember it's flattened, why? Because area under the curve, F, must be 1. So if there's a squeeze, right, it must be taller. It must flatten out, must be shorter because area must be 1. Okay. If you just move, compare the green and the blue, the same fatness, and only the mu to just move a little bit back. Okay. So you will say in statistics, mu is the location shifter, moving left or right, right? Positive move to the right hand side, negative location shifter. And the sigma is a shape shifter, right? It's getting don't move location, but you just bend, you just fatten it or heighten it. Okay, these are mean and variance. Okay, so basically for this normal, only two number, mean and variance. Okay, and tells you two things, right? And interestingly, mean and variance are separate, can be controlled, right? Remember, binomial is not. Because binomial is n and p, two things, right? And mean is np, variance is np times 1 minus p. So if you change the mean, likely variance change as well, right? Because you increase n, or increase p, or decrease p, both of them will change. But for the bell, interestingly, they're different. Controlled by different thing. Okay. Okay. So we can see, although I put this in the box here, but I will never ask you for this. Okay. There's no way I ask for this guy. Okay. I put it there because if you want to do the proof, that will be there. But the only thing is this is the mean, this is the variance. Okay. Is that okay? So I wanted to talk about this slide that is conclude today. Okay. So what are the application? I already mentioned many already. I mentioned last one already, what we call the central limit theorem. We said if the random variable, okay, is the result of many independent things, then it's a bell curve. Okay, this is something that we will actually learn it later in our course. The second is what I just said from the physics. Okay. If you imagine this is empty space, okay, and it's actually quantum mechanics, right? Where the location of the particle, okay, and it only depends on the center is here, right? Where it can be, right? You can imagine electrons, right? The electrons is actually probability, right? And the distance is virtually this point. How likely is it? Depend on how far from distance. Doesn't matter. In this circle, the same probability. That's why I said, no matter how you cut it, the same probability. And these two dimensions the same, whether x and y doesn't really matter, right? Because the dimension is just you decide what's the dimension, right? So that means that no matter you rotate the sx, whatever, the same, then this follow normal. Okay, so that's why normal is very natural, even you go to engineering, right? So it doesn't depend on how far where the electron is, right? It really depends on where they are. And the other thing with the last one is what you call approximate binomial or Poisson. Okay, if you have binomial when n is very large, that will go to bell curve. So we can forget about binomial because bell curve solve the problem. Or your Poisson, the same. If lambda is very large, then also bell curve. And also actually hypergeometric the same. If you have a large sample, also bell curve. Okay, so that's why everything go back to bell curve. That's why the bell curve is the single most important thing you want to learn in this class. Okay, so I will see you next Monday. Enjoy the weekend.